Hello and welcome back. My name is Constantine, and today we're going to go through a very interesting problem: binary tree vertical order traversal. This is a very cool problem just because the first time when I solved this problem, I got to learn a new concept. Hello and welcome back, everyone. My name is Constantine, and today we're going to go through a very interesting problem: binary tree vertical order traversal. This is a very nice problem, and the first time when I solved this problem, I got introduced to the concept of pair in Java. So it's basically as a tuple in Python when you're returning two values. So let's see how we can solve this problem. Given the root of a binary tree, return the vertical order traversal. So from top to bottom, column by column. So in the first example right here, we know that this 9 comes first just because we need to imagine basically as columns. And the second column is 3 and 15. The third column is 20 and the fourth column is 7. And if we're looking at other examples right here, we could see things could get a little more complicated just because we have more levels and more nodes. And let's see how we can solve this problem. Let's get to our whiteboard, and I think this is a very interesting problem. And once you solve it, you just learn so much from this problem. So this is our tree. So we need to return basically 4. So think about this. We need to return 4, right? And then 9 and 15, and then 3, 0, and 1, 8, 2, and 7, right? Good. So I think it's clear at this point what exactly we need to return, but how are we going to do this? So again, since this is a tree, we know we could do BFS or DFS, right? So for this purpose, I think if you've done levels by level traversal, just a classic BFS where you return these kind of like each level, then we know that probably the easiest way, at least in my opinion, is to do a BFS. Good. So now we know that we need to do a BFS. We need a queue, right? So we add a node and then we add its children and so on. So I want you to think about this tree as a matrix. So think about this. Let's try to draw this tree inside this matrix. So right here in the middle, we would have node number 3, and then right here we would have 9, and right here we would have 4, right? And on the right we would have 8, 7, and then 5 would kind of like be at the same position. 2 is here, and then in the middle right here on the same level with 3 is 0 and 1. Right? So do you see anything here? Do you see anything here useful? And this is what we could even, I'll give you another hint. Just imagine this is a column 0, and basically we're going towards the left. So this is -1, this is -2, this is 1, and this is 2. So now all we have to do, if you see that, we have to store, we need some sort of data structure where we could think about, oh, at this index right here at -2, we have element 4. At this index of -1, we have 9 and 5. At 0, we have 3, 0, and 1, and so on. So if you were thinking about a hash map, then you got it right. A hash map, it's a very easy and very nice way to store this kind of like key value pairs. So we would create a hash map, right? And our hash map would have a indices of the column basically where we found this node and a list of integers, just because we could have multiple integers, multiple nodes at the same level. So in our case, if we would start from the root, we would go ahead and put our index first index will be equal to 0, and then our index at position 0 we know we'll always find only the root, so it will be equal to 3. Then we'll go again and since we're moving towards the left, we're going to decrement this initial position. So now at position -1, we're going to put 9. And then moving again at position position left again, we're going to have -2, and then we're going to put 4. And then again, from this 9, if we're moving to the right, if we were right here, we're going to put at position 0, because we're incrementing, we're going to put 3, right? So now we're going to put the 0 right here. And then, and so on. So initially, our map is, we're starting from the root right here, and this is always at position 0. So at the end, how our hash map is going to look something like this, right? So we're going to have another 1 right here, and then we have 1, and the values are 8 and 2, and then we have 2, and the values are 7. So this is how our hash map will look. So right now it's easy to say that all we have to do is traverse this hash map and kind of like sort it, right? We want to print out the smallest values first. So -2, that's the smallest value in our hash map. So we're going to print 4 first, and then we're going to print 9 and 5, right? And these are all lists. So what's our time complexity if we sort this? So if we sort our hash map, I think the whole problem itself we managed to do pretty well, but then our time complexity is just going to be ruined because we need to sort this hash map, right? Because it's going to be n log n. But we could even do better than that. We could just do time complexity of n, just because we would keep 2 variables, minimum or max and maximum. And each time when we're going to decrement, when we're going to go to -1, -2, our minimum, it will be the smallest value. So at the end, after we have our hash map, our minimum will be equal to -2, and our maximum, so these basically are 2 values for which we know the hash map keys are going to be between these 2 values. So our max will be equal to 2. And then at the end, we could just iterate between min and max and just print the values from the hash map itself. Good. Now let's go to Leetcode. Let's try to code this up super quick. I hope once you figure it out that we need to use a BFS, and if you can come up with this matrix implementation, not implementation, but visualization, I guess more. Just imagine this tree is a matrix. And once you got that out, you always know that your root is going to be at column 0, and to the left, everything is minus, to the right, everything is plus. So once you kind of like are able to visualize this, I think the problem is it becomes much easier. So let's go ahead and try to code this problem right now. So we know for sure we need to return a list of integers, right? So we can just declare this right here, and we're going to call it result new array list. And then we could even check, we could make an extra check if our root is null, then we could just return our result. Good. So now we said since we're gonna do a BFS, we know we need a queue, right? So let's go ahead and create a queue, and we're gonna use the inbuilt class of Java pair, which is gonna be able to hold a tree node and a position, the position of the column. So in this case is gonna hold this 9 at position -1, because we need to know which position we found this 9, which position we found this 2 in this kind of like matrix whatsoever. So let's go ahead and add in our queue a pair, which is gonna hold a tree node and a integer, which will be our position. And we're gonna call this queue equal new array dq. Good. And at this point, if we made it through the first if statement, we know that our root is not equal to null. So we could even just go ahead and actually, just before we adding it, let's create a variable which we're going to call column. And initially, we know for the root is going to be equal to 0. We'll always start from this column right here because that's our root. So basically, that's exactly in the center of our tree. So now we can add our root to our queue. So we're just gonna have queue add, and we're gonna add a new pair, and we're gonna pass our root and our column. Good. So now we said we also need a hash map, right? So it's gonna store the index of the column and the list of all the nodes that we found at that column. So we could go ahead and create a hash map which will hold a integer and a list of integers, just because we could have more nodes at that index. And we're just gonna call a map, new hash map. Good. So two more things that we need to add just before we start traversing. We start iterating through the tree. We need to have a min and a max, right? So remember, we need a min and a max because we need these values right here in order to save us, like to improve the time complexity and not sort this map at the end. We could just keep a min and max, and then at the end we're just gonna iterate between min and max. So let's go ahead and do that as well. So we're gonna have an int min equal to integer max value, and we're gonna have an int max equal to integer min value. Good. So now we're gonna start processing our tree. So while our queue is not empty, now we already added this one to our queue, right? So right now we need to poll it to remove it so we see actually what node we had in there before. So we're gonna get a pair tree node integer, and let's just call it pair, and it's gonna be equal to queue that remove. So we're removing whatever we had so far, and we could even do tree node current equal pair that get key. So when you create a pair of tree node and integer, the way to access the first element right here is get key, and the second element is get value. So it's exactly like almost like a hash map. You can just store a key and a value. So, and we'll have an integer, we'll have our column is gonna be equal to get value. So right now our column right here is 0, right? Just because this is how it was initialized. So once we've done that, we could go ahead and check our mins and max. So min is going to be equal to math.min between my column and my min, and max is going to be equal to math.max between my column and my max. So this is just to keep track of these two variables right here. Good. So now after we've done that, we need to check if we have seen this element in the map. Have we seen this column? Have we seen this column already in the map? Because if we had, in this case, for example, imagine that we put -1 and 9, then we need to put -1. We need to put 5 at -1. Again, at the same key. If we haven't seen the key, we're just gonna create we're just gonna put the element itself. So we're gonna make two checks right here. So map put if absent. So map put if absent our column, and if it's absent, we're gonna create a new array list. And if it's not absent, we're just gonna get it, map get column, and we're gonna add our current node. And since our current node is gonna be the value is gonna be an integer, we're just gonna add it to our map. And after we've done that, we only have to make two more checks, classic BFS. So if current.left is not equal to null, all we have to do is add it to our queue. So queue add new pair, and we're gonna pass our current.left. So we add current.left, and then column -1. So you see what we're doing right here. So we're adding column -1 just because we're going to the left, we're gonna decrement column. We started at 0 and we're gonna go -1, -2, and so on. And on the right, we're gonna increment our column every single time when we go to the right. So this is for our left, and we could even copy and paste exactly the same thing, and we're only gonna change left to right. Left to right, and column +1, because we're gonna increment our column in this case. So after we've done this, all we have to do is add our result into our result list right here. So we could just have a for loop, and we know we have to start for in I equal to our min, because that's the lowest key in our map. I less than our equal to our max, I plus plus, and then we're just gonna add it to our result. So result add map get I. So at the end, we could just return our result. Let's put an extra space right here just to be more readable. So that's it for this problem. In this way, our time complexity is basically O of n, just because we're going through each of the nodes and we're adding into a hash map. We're looking in a hash map, and after we constructed all our hash map, we're just gonna print its values. So let's give it a try. That's I think it will work fine. So that's it for this problem. I think it's very cool. It's a very cool problem. You get to learn a lot of it. I didn't know about this pair where you could just add a key and a value, and you could access it with get key and get value. That was a new learning for me. But I think this is a very interesting problem, and once you're doing it, you're gonna become so much more comfortable with BFS and with the notion of traversal of a tree. So thanks for watching. If you feel like you learned anything from this problem, please consider giving me a thumbs up and subscribe. Why not, if you think you want to see more videos like this in the future. Thanks, and see you in the next video.